Second speaker of this session is Takafumi Arakaki from the University of Oregon, and he will talk about transducers, data-oriented abstraction for sequential and parallel algorithm on containers.
Okay, thanks. So I just uploaded my slide, and I think could be my slide could be small for the audience on the back, so you can just go there and then should be able to read the code. So this is the title of my talk when I submitted it. Transducers, data-oriented, blah, blah, blah. It's long. And while preparing it, I just realized that my message is a little bit different and simple. So foldl is great. Foldl is great. Let's use everywhere. So to restart my talk, my name is Takafumi Arakaki. I know as TKF in GitHub and other places in internet. I work at University of Oregon as a postdoc. My day job is neuroscience and doing mathematical modeling, and so lots of math and code programming. But today's talk is little to do with my day job. It's more to do watching YouTube. I mean, not during work, not during work. So I just stumbled upon this talk by Transducers by Rich Hickey. He's a creator of a language called Clojure, and he invented this thing called Transducers. And after I watched this talk, the high-level explanation of what transducer is something that can implement a map or filter without referring to explicit containers like arrays. But that sounds a little bit abstract and hard to grasp, and that's actually what I felt after watching this talk. And I implemented this in Julia, and then re-implemented it several times until I realized that this is really could be used for framework for Julia. So I'm here in JuliaCon and to talk about it. So I will introduce transducers by kind of deriving it, or like pretending that I'm deriving it. And then I'll talk about characteristic transducers. And as I said, it's something related to map and filter. You may be wondering if it's related to like iterators. So I would kind of contrast to iterators as well. And after the end of the talk, it should be, I think it'll be clear why I'm thinking that it's appealing to Julia. So what are the transducers anyway? So my simplest explanation is that transducers are the transformation of loop bodies. Okay, so it's still unclear probably, so let's see some example. So this is like very simplest some function, I think, and I'm sure you can write better than this because I'm using literal 0, so no type stability there, but don't shoot me. So this is one simple example. Another example could be like a map of f. And it's simple. You just take f of x to output vector, right? Okay, so let's tear those functions a little bit. They're more or less the same, right? Structure and everything. So they both accumulate an object. So for the sum, it accumulates a number. And for the map, it accumulates a vector. So let's rename those to ACC for accumulator. As you can see, the main difference is in the loop body. So let's restructure them like this. So in sum, I explicitly apply plus function and reassign it to ACC. And in map, I applied the push function and reassign the return type to ACC again. This is okay in Julia because push returns the first argument as is. Okay, so now we are ready to factor out the loop body. As you can see, both function apply some function to the element of the vector and stick it to the second argument to some function. So we can just extract this structure out to a higher function. Let's call it mapping step. So it receives function f and some 2-argument function step, and apply function to f, and then put that result to the second argument of the step. So with this function, we can just extract out, oh, by the way, there's another way very short way to write it in Julia. You can use anonymous function. If you're familiar with functional programming, probably that's easier to read, so I will put it there as well. So using this mapping step function, you can factor out all the complex things going on in the loop body and then force this out of the loop. Okay, this is great because now the loop structure is completely identical, and not only that, this loop is called has a name and it's called foldl. Okay, so with this mapping step function and foldl, we can finally refactor things in sum and map. So for sum, we apply mapping steps with compose plus with using mapping step, and then for map, we compose mapping step with push and apply feed the appropriate initial condition, initial value like 0 for sum and empty vector for map. Okay. So, okay, this probably look like very kind of weird way to write simple function like sum and map, but let's see if we can like extend this to other functions like filter. So we try to do the same trick again to extract out the loop body of the filter. So let's create this filtering step function and then just going to copy the loop body into a function body new step, or function body of the new step. And then we can use this filtering step function with the filter, and it works as like the original function filter. Okay, it's so far so good, but there's a problem because those filtering step and mapping step don't compose well. So here I'm doing in this make step function. So first I filter out missing value, and then decrement by 1, and then filter out non-positive values for some reasons. And it's, oops. Where is it? Okay, sorry. Wait, no. Yeah. So as you can see, this make step function is ugly because there's like nested level of call chains and doesn't compose well. So, but it's still nice in the sense that I can use this make step function with a plus function or push function to compose them with step function like plus and push. But to make this make step function a little bit better, I can do a little bit strange thing, which is just pushing another, inserting another closure. So in this mapping function, so this mapping function returns a function called transducer, and then inside transducer, it creates new step function and return it. So like one level of interactions there. And yes, so this is the simplest version of a transducer, and you can kind of see why it could be better for compositionality, because the transducer receive a step function and return a step function. So yeah, it could be better for compositionality. Okay, let's do the same trick for filter. So we again insert this transducer as a closure, and then transducer in turn transform old step function to the new step function, right? Okay, so let's see how it works. So first 2 lines, just again the definition of mapping and filtering transducers. This XF is how I compose those transducers. So first I filter out missing values, decrement by 1, and filter out non-positive values. to use this XF, I can just evaluate this on plus function or push function and just pass it to folder, and it just works. Okay, so here is another challenge. Can a transducer truncate inputs? Or in other words, can it terminate the loop? So let's try to implement this take while function. So it will collect the value while this f of x evaluates to true. Okay, so let's try it. So if branch is easy because it's what we did in the filter. So if fx true, then we just evaluate this step function and return the thing as is. But the problem is what to do in this else block. How do we like break out the loop? So this is problematic because foldl is doing the loop outside of step function. So like there's no way to bail out the for loop. So we need to change for loop a little bit. So I introduced this reduced type and change the foldl in such a way that so after applying the step function, this foldl checks if the arc is reduced or not, and then if it's reduced, just bail out, and then if not, just continue the loop. And I want to point out that this works great in Julia because if the compiler can prove that arc can never be reduced, then this if branch is completely compiled away. So this is like there's no runtime cost if you're not using it. That's great. So this is the implementation of taking while transducer. So instead of break, I can just use return reduced evaluated on ACK. Okay, so far I explained that transducer and extended foldl can do many things like mapping and filtering and termination. So today I don't have time to show other things, but believe me, it can do like filtering, so the nested for loop, and as well as like composition of stateful computation like scan. But you may still wonder if it really shows that transducers and iterators are equivalent or like have the same power. It turned out actually that this question is a little bit misleading because transducers and iterators are not the counterpart of each other. So to ask the question, we need to define some terminologies, and then this is what I came up with. So iterator is defined by base.iterate function in Julia, and then this actually corresponds to reducing step function in transducer and foldl framework. So, and you can kind of see that they are related in a sense dual to each other. So iterator maps old state to new state and new output. And in the foldl, reducing step function maps an accumulator and the new input to the accumulator. So you can kind of see that the function signature are flipped when going to the other framework. And the iterator so what I call iterator transform is mapping from iterator to new iterator. So it will be, so for example, using map, it's the function where I fix the first argument of this map function. And then for the transducer, it's related to mapping of f. And in both frameworks, there are mechanisms to run the loops. So in iterators, it's just for loop is provided at the language level. And for the transducer and folded, it's just folded function. Also, I should mention that this is the result of like long discussion with John Widner in GitHub issue. So if you are familiar, if you want to like look into like more formalism in like kind of category theory thing, I would recommend checking out this issue. It was interesting. Okay, so now we can ask the question. So are transducers equivalent to iterator transforms? That's the valid question to ask, and the answer is yes, because I can write the function to convert iterator transforms to transducers, and transducers to iterator transforms. So, okay, so I can write it, but it's long, so you probably cannot see it. But the other direction, transducer to iterator transforms, is easy because in Julia I can just use channel. There's something called induction in transducer JL that does that, but without using channel and a little bit more efficient. So, okay, so that was transducers and iterator transform. So how about for loop? So to see the relationship, it's easier to define a function called for each. There's for each in the base, but it's also very easy to define it from foldl. So it's just kind of trivial transformation of single argument function to reducing step function. So given single argument function, I just call it inside of reducing step function. And so it is useful only with side effect function, but you can write it in way closer to for loops. Okay, so using this function, I can just map Julia's native for loop to this for each. And not only that, I can also implement something like for else block, as in Python else block, and also break with value, as in Rust. So the syntax is a little bit busy because I don't have language-based, language-level syntax for it, but I hope the relationship is very clear. Okay, so I took like 20 minutes to like explain transducers and iterators are like equivalent, and you may be wondering why you should care, because if they are powerful enough, then as powerful as iterators, why should you use it, right? So I would argue that the reason is performance, because I think there's more optimization opportunities in foldl than in iterate. And that will be clear if you look at who implements what in both frameworks. So in iterators, container authors implement base iterate function, and container users use them in a for loop. In transducers, user implement reducing step function, and container authors implement foldl. So the foldl advantage is that container author libraries are the best person to implement the loops. For example, container author can use their knowledge about containers, like type constraint and the memory layout, to schedule the best looping strategy in the foldl. So the best example, I think, is from the vcat or lazy arrays. Vcat is lazy version of usual vcat, but it keeps the original arrays as is. So, for example, if I put static vector or unit range or normal vector, it keeps those object as is, and I can access it by this arrays field. And writing foldl is quite easy because I can unroll all these loops. And you can see that that will help compiler, because, for example, if the element type of these arrays are different, reducing step function can be specialized or like dispatched onto this type, and then this will happen to compile time, and compiler will inline it if it's possible. So it will, you are paying no cost at runtime. And also this kind of unrolling helps CPU because the state of the iteration is encoded at a position of the code. So like it's the extra help. And not only that, you can also specialize a looping strategy for each array type. So you can call foldl inside of foldl, and then it will use specialized looping strategy for each sub-chunk of these arrays. Okay, so it was, I was using some kind of pseudocode there, but like this is the real example. For example, so for the like simpler case where I have vector of vectors, That will be the this will be the we are called uwrite. So I will create this custom struct to wrap vectors of vectors, and then define this foldl double underscore foldl function. So this is my overloading API, and then write this very straightforward nested loop to loop over vector of vectors. This add next, so there's this add next macro, but it just expands to very simple few lines of code. It just checks if the reduced, if the value is reduced and the bailout if it is. But I would say that this is still simple even with these, even without macro. And the bonus is that it's pretty simple to, for example, support SIMD. You can just stick SIMD into the innermost loop, and then yeah, you will get the extra benefit of SIMD. On the other hand, defining iterates is pretty challenging for something like vector. So it is hard to write and perform worse, and then also to support SIMD, you need to write very different functions to do it. And so far I was talking about the properties of containers, but properties of reducing functions is important as well. So for example, if it has associated property, you can parallelize it, and if it has commutative properties, you can reorder the iteration order. And transducer property also interact with these algebraic properties of reducing functions. So some property can break these, and you can check that if you can use some special fold. So this is one example. So if you can prove that reducing function is commutative, then you can reorder the iteration, and then use, for example, in the case of matrix multiplication, you can choose the fastest axis for each arrays that involved in innermost loop, and then use that to iterate over those pairs of items. I made this API, but it's kind of interesting because there's so little for each user can do. They can like specify the pairs of index, and then they can specify the loop body, but that's it. For example, they cannot even do the indexing, so they cannot so the add inbounds, for example, happens automatically there. And there's so much foldl implementer can do, like maybe like parallelization or like cache obvious access pattern, or thing like that. Okay, so to summarize, Julia ecosystem has a rich set of custom arrays and containers, but iterators cannot be used to efficiently iterate over those custom arrays. But foldl, so maybe the best API to capture these diverse requirements of these nice custom arrays. Unfortunately, foldl is not good enough because it doesn't support break, and then you don't have rich iterator transformation functions like filter from iterators module. But extended foldl and then transducers solve these problems, so there's nothing preventing you to use foldl now. So let's use foldl. Thank you.
Hi. Thanks for the talk. Do you think for loops are the new go-to? Will they just be extinct someday?
So yeah, there's not much time to like compare really iterators and folder approach. There's so iterators are dual over transducers, so it's good at when you're receiving values. So if you want to, for example, create, if you want to fill the vectors, then you may want to batch like the extent of a vector and then fill them like chunk by chunk. This is very easy to do in iterators because you control the for loop, and it's difficult to do in transducers because this is other way around. So I think it will be case by case basis, But my argument will be that you will be reducing values more than creating arrays. So yeah, for loop it still has some use, but I think foldl will be a nice default for user to use.
Yep.
What about the space usage?
Pardon?
The memory usage?
Memory usage. So foldl and compose with transducer will it will compile down, so it will inline and compile down to the code you would write even without it. So I don't think there is extra penalty by using foldl. Okay, good points. So there's a kind of fake support right now in Transducer to use in GPU, but it's hard to do with stateful transducers that I didn't have time to explain today, because so things like mapping and filtering, that's pretty easy to use with GPU, and then it's doable right now already. Yeah.
Could you elaborate a little bit on how you handle multiple dimensions in the data?
Oh, thanks. So yeah, that's related to GPU question, I think. So if transducers are not stateful, you don't have multiple state to handle. So that's pretty easy, but that's kind of easy answer. But if you want to if you want to do terminating transducers and stateful transducers, that I think that's very difficult, and I'm not sure if you want to do it. Because if you are processing multiple dimensions at once, what kind of break kind of semantics you want? Do you want to break when one of them fail, or want to break all of them fail? So that's kind of semantics is not defined at the moment, and then that's at the moment I don't know how to do effectively right now, but once you define the semantics and then maybe way to choose semantics, I think it's doable, and then it's interesting in the future direction.
Couldn't you use a filter to sort of, on the multi-dimension case, right?
So if you use something like what's called iter call in iter rows, I think now in base, that if the reducing step function receives the whole vector as is, then the multiple dimensional fold will be it's kind of equivalent to scalar fold, because you're kind of receiving one vector at chunk one by one. If you want to kind of vectorize given reducing function, given filtering reducing function, actually, so filtering is easy. Sorry, filtering it can be done, but terminating and scan is hard. So yeah, filtering works right now. You can just Transducer gel now supports QRAs, so you can just use it. Yeah.
Let's thank the speaker again.